Thank you for attending my talk. I really appreciate your presence here. And the rough plan of the talk will be the following. I will start with the main definitions so that you understand what the general setup in algebraic geometry is. And then I will tell a story about higher Fano manifolds. So this is our group of collaborators. This is me, and I know that I have different hairstyle from this picture, but I will be citing our paper with these people a lot. So it's just nice to see all of them. And also when I cite this paper, I will say the word team instead of writing 8 initials. So in algebraic geometry, we don't usually worry about the field being C, as long as it's algebraically closed and usually characteristic 0. But in order to preserve some geometric and topological intuition, I will assume that everything is over C. And X will usually denote a projective manifold. So a manifold means that it's a complex manifold, and the fact that it's projective means that it is given by some polynomial equations inside of CPN. On this manifold, we can consider vector bundles, and vector bundles of rank 1 are called line bundles. And these line bundles form a group under the operation of taking tensor product. So pick X, called Picard group, will be our notation for the group of isomorphism classes of line bundles.
So closed here means closed in the Zariski topology?
The topology, closed in the Zariski topology in this case will also be closed in the usual topology. But yes, when I say that it is given as a set of solutions of some polynomial equations, it automatically implies that it is a closed subset in the Zariski topology. When we talk about manifolds in algebraic geometry, we usually try to classify them. And as a toy example, we can consider the case of curves. So these are manifolds of dimension 1. And dimension 1 over C corresponds to dimension 2 over real numbers. So complex curves are also known as Riemann surfaces, and they admit a topological classification into 3 types. So the first type is genus 0, and the only genus 0 curve that we know is a sphere. And we know that a sphere has positive curvature. Genus 1 curves can be thought of roughly as a surface of a donut, a torus. And they have 0 curvature because we can also think of them as we take the projective, the complex plane, C, and if we pick a square or a rectangle on this plane, we can glue the top to bottom sides and the left to right side. So this will give us the flat metric on the torus. And curves of higher genera are known to have negative curvature. This is a more differential geometric characterization of these 3 types. And I am more interested in invariants that are that live in the algebro-geometric side. And so I can take the tangent bundle of X. And in this case, the determinant of the tangent bundle will be equal to tangent bundle itself. Yes?
How come the argument that you made for the torus doesn't work for higher genus things? Those are quotients of polygons as well.
That is true, but if we want to take a constant curvature space, we take these polygons to be polygons. So first, every angle in this polygon should be a right angle, so that when you glue 4 of them together, you get the whole like 180 degrees. And to achieve that, you need to put them into the hyperbolic plane. So these are hyperbolic polygons. Thanks for the question. Here, the determinant of the tangent bundle is equal to the tangent bundle itself, because on a curve, the tangent bundle has rank 1. And in genus 0, the determinant is very positive and actually ample. I will explain what it is on the next slide. In genus 1, the determinant is trivial. The tangent bundle is trivial because, again, in this quotient picture, we know that a rectangle has a trivial tangent bundle, and if we check the gluing conditions on the sides, they will be trivial. And the tangent bundle on a higher genus curve is negative in a sense, or we can also say that its dual is ample. And another invariant that we consider is the Picard group, the group of line bundles. In the case of genus 0, so this is CP1. CP1 has a discrete Picard group, which is isomorphic to Z. While Picard groups of higher genera curves have several continuous parameters. So here is the definition of the notion of positivity that I will use a lot in this talk. So considering, again, a projective manifold and some line bundle on X, we say that L is ample if we can take some power of this line bundle. So L tends, and take its tensor power n. Then we should have enough sections in this line bundle that would give us a closed embedding into a projective space. Does it give the rough idea? Can I continue? And with this notion of positivity, we say that a manifold is Fano if the determinant of the tangent bundle is ample. And the first property is that a variety is Fano. A manifold is Fano if and only if it admits a metric with positive Ricci curvature. Yeah. So this is analogous to our characterization of the genus 0 curve. Also, we can find in the literature that a Fano manifold is simply connected. Its pi 1 is trivial. And using this fact and the exponential sequence, we can prove that the Picard group is free and finite rank, which is analogous to the property of CP1, that the Picard group of CP1 was Z. In this case, it means that it is Z to the n.
Sorry, this means X is Fano if and only if all 3 of these are satisfied?
No. By definition, X is Fano if the determinant of the tangent bundle is ample. And if and these are the facts that hold true for Fano varieties. So the first fact is that this definition is equivalent to requiring positivity of the Ricci curvature. And these two are properties of Fano varieties. And with this third property, we can observe that that the following two invariants are well defined. So rho x, which is the rank of the Picard group as an abelian group, is well defined. And also we can define the index of a Fano variety x. Like so, the index is denoted by R. It will be the maximal multiple of some line bundle that gives us the determinant of the tangent bundle. So in other words, you can think of it as a number that describes how divisible this determinant is inside the lattice pic x. And there are some more nice properties of Fano manifolds, which signify how important they are and why there is so much attention, and why people pay so much attention to them in algebraic geometry. So there is a classical result by Mori that X is covered by rational curves, and by a rational curve, I mean an image of CP1. So we map the projective line inside our to our X, and we want this map to be non-constant. And I actually don't care if this curve, this CP1, self-intersects inside X, or if it becomes singular. Then Kolar, Miyaoka, and Mori proved that Fanos are rationally connected, meaning that for any 2 points, we can find a rational curve that passes through through these 2 points. And further, in fixed dimension, they form a bounded moduli. So this means that if we fix a dimension of our manifolds, then there will only be a finite number of deformation classes, of deformation families of these Fano varieties. And there is a nice classification, a nice series of classification results by many people. So the first results go back to Kobayashi and Ochiai, who proved that the index of a Fano variety is at most n+1. So if we have a Fano variety of dimension n, then the determinant of its tangent bundle is divisible by at most n+1. And further, index is equal to n+1 exactly when X is isomorphic to CPN, which is a pretty interesting characterization of projective spaces. They also proved that index is equal to n if and only if X is isomorphic to a quadric in a projective space, meaning a solution of a degree 2 polynomial equation. And then there are further results due to Fujita and Mukai, who gave full classification for index n-1 and index n-2. And Wisniewski provided some classification for index at least n+1/2. So requiring high index for a Fano variety gives enough restrictions to characterize them to come up with a classification. Yes?
What are being covered by curves mean?
It means that through every point of X, there passes a rational curve. So it is a simpler property than the second one, because here we require that through every 2 points, there is a rational curve that connects them. Here we just want for one, given 1 point, there is a rational curve through this point. We don't require that it connects it to another point.
Is this natural in the sense like the maps irrational curves, which are covered by that. It's basically like a canonical choice of if you can be a point inside X is very canonical choice of the rational curve, or is this
a canonical choice?
natural?
I wouldn't say there is a natural choice of a rational curve, because the point of this of the second result is that there are a lot of rational curves on Fano varieties.
Right, and there's no way to pick a good one. All that.
I wouldn't say so. Like, especially if you think of CPN, it has so many symmetries that, like, how would you pick a line on CPN?
Does the first point follow from the fact that these are all subvarieties of CPN?
No, we can come up with some subvarieties of CPN of high enough degree that there will actually be not a lot of rational curves on them. And now we know that Fano manifolds satisfy a lot of nice properties, so it would be good to know some non-trivial examples. And the first example is the projective space is Fano. And the Grassmannian, which is a manifold that, like, whose points correspond to k-dimensional subspace in an n-dimensional space. It is also a Fano manifold. Further, if you consider hypersurfaces in a projective space, as long as they are of degree at most n, they will be Fano. And I also assume that these surfaces are smooth so that we stay in the world of manifolds and, like, not go to varieties. And complete intersections of low degree in projective spaces or weighted projective spaces are also Fano. And by a complete intersection, I roughly mean an intersection of several hypersurfaces which intersect transversely. Another example is called a rational homogeneous space. So it is the quotient of a group G, which is a semi-simple algebraic group, by its parabolic subgroup. When you say a parabolic subgroup, it means that the quotient is compact as a topological space. And the basic example is when G is SL2 or SLN, and for SL2, P can be chosen as the upper triangular matrices, or more generally for SLN, it can be block upper triangular. Going back to our trichotomy for ribbon surfaces, we can remember that Fano varieties are characterized by having positive curvature. So the only curve that is Fano is CP1. And in dimension 2, Fano manifolds are called Del Pezzo surfaces. And there is a complete list of those. So we have blowups of CP2 in k points for k ranging from 0 to 8, and the product of CP1 cross CP1. So here with the blowup in 0 points is just CP2 itself. And when I say that we blow up a point on a surface, it means that roughly we take this point out and replace it by a projective line. And we can choose up to 8 points in general position to get a Fano manifold. In dimension 3, there is a complete classification that is available online. And if you see it, you will understand why I didn't put it on the slide. So they give classification by the pk rank, so like pk rank 1, pk rank 2. And you can see that there are a lot of examples and deformation families. Are there any questions about examples? Okay. Then I would like to move on to defining higher Fano manifolds, which are manifolds with an even stronger positivity condition than Fano manifolds. And for this, I will need to remind you what Chern classes are. So again, if X is a projective manifold, and let us pick a vector bundle V, its first Chern class is defined as the vanishing locus of a general section of the determinant of V. So we take the determinant of this tangent of this vector bundle, we take some section, and we take the zero set of this section. And the Chern character of V can be characterized axiomatically. So it satisfies additivity. If we have a direct sum of two vector bundles, then Chern character will be the sum of the Chern character of the two summands. And it is multiplicative with respect to tensor product, where here this dot means the intersection product. So I think of Chern classes and Chern characters as some closed subsets inside X, and I can intersect these closed subsets. And further, we say that the Chern character of a line bundle is the exponential of the first Chern class of L. So here, for example, C1L squared would take two general sections and take their intersection. And I claim that this is enough for calculations, and it is not necessary to see the construction for this definition. And using these invariants, the Jong and Starr defined two Fano manifolds as Fano manifolds which have positive second Chern character. So in terms of Chern classes, the second Chern character can be expressed by this formula. In terms of the axiomatic definition of the Chern character, we take all the summands inside the Chern character which have codimension 2. And positivity means that for all surfaces inside of X, the intersection with the codimension 2 component of the Chern character is positive, meaning that the intersection is going to be some combination of points, and we want the number of points counted with multiplicities to be positive.
How are you thinking about this Chern character as a sub-variety of what? The dependent one?
I think of it as a combination of closed subsets inside X. So I would write it as so CH of V is going to be CH not of V plus CH1 of V plus CH2 of V, and so on. And so the only codimension 0 subset of closed subset of X is X itself, assuming that X is connected, which is my usual assumption. So Chern 0 of V, I can think of it as a number because it gives us the number of times that x is counted. And this number is actually equal to the rank of V. Chern 1 of V will be a linear combination of codimension 1 subsets. So it can be something like 2d1 plus 5d2. And Chern 2 of V will be the linear combination of codimension 2 subsets. And going on up to CHK, we can say that X is K-Fano if it is K minus 1 Fano and CHK is positive in a similar sense that its intersection with a K-dimensional subset is going to be positive. Any more questions? Because if we intersect enough times, so if we go up to codimension n, it will be a linear combination of points. And if we intersect any more, we will get 0. It means that Chern character of in degree n plus 1 and higher will vanish. And it means that if X is K-Fano, then its dimension is at least K. And now we can consider some examples of higher Fano manifolds. So in dimension 1, by this observation, there will be none. So there will be no 2 Fano manifolds. In dimension 2, recall that we had a list of Delpezzo surfaces, which was actually just 10 of those. So by checking those explicitly, we can see that only CP2 is 2 Fano. Then there is a nice fact that if X is a direct product of 2 positive dimensional manifolds, or if it is a CPK bundle, then it is not 2 Fano. And here I also assume that K is positive and the basis is positive dimensional, just to avoid the trivial cases. And using this fact and the list that I showed you online, Carolina and Anna Maria provided classification of 2 Fano manifolds of dimension 3. So like dimension 3 manifolds are often called threefold. So these are, so the only 2 Fano threefolds are CP3 and a quadric in CP4. And if we write out what the Chern character of the tangent bundle of the quadric is, we can check that it is not 3 Fano. So the only 3 Fano is CP3. The only 3 Fano threefold is CP3. Further examples include the following. So Carolina and Anna Maria proved a classification of 2 Fano manifolds of high index. So for dimension at least 3 and index at least n-1, the 2 Fano manifolds are either the projective space or a complete intersection of low degree in a projective space or a weighted projective space, and they give explicit bounds on the degrees. Or they give 4 examples of rational homogeneous spaces, G mod P, and for one of those homogeneous spaces, several of its hyperplane sections will also be 2-Fano. And they prove that this is the complete list of those. So with our group, we further checked which of those are 3-Fano. And the only 3-Fanos of high index are actually only complete intersections of low degree. And we again give an explicit bounds for the degrees. Also, we provided a complete description for which rational homogeneous spaces of pk rank 1 2-Fano or 3-Fano properties are satisfied. And we can look online for a visual summary of our results because writing it out on a slide would look messy. So in this table, we see the beginning of a classification of rational homogeneous spaces of pk rank 1. And the light gold color corresponds to those that are 2-Fano, and the dark gold color corresponds to those that are 3-Fano. And we can see that the only 3-Fano manifolds among those are either projective spaces or quadrics. And so there are no 3-Fanos in the exceptional cases. And so to sum up, we actually don't know examples of 3-Fanos which are not complete intersections, and this is still an open question. And further, if you look at if you do the calculation for complete intersections, then with this bound on the k-Fano property, you can check that this establishes that X is a projective space. But for not just complete intersections. So if X is an arbitrary k-Fano, in general, it is not known if the bound that X is n-Fano and dimension n. We don't know if this implies that X is a projective space, although we would expect that it does. Any questions? Okay, so here is why higher Fano manifolds are conceptually interesting. They are an attempt to draw a parallel with the topological notion of connectedness and higher connectedness. So in topology, we can say that X is path connected if for every 2 points there is a path through X and Y. And we can give a similar definition of X being rationally connected if for every 2 points there is a rational curve passing through these points. Also, we can in topology we also have the notion of simply connectedness, and simply connectedness means that X is connected, and pi1 of X is trivial. The fundamental group is trivial, but in algebraic geometry we don't have the notion of a fundamental group that would recreate a nice object. So since we have been talking about manifolds, we would really want to obtain something that is also a manifold. But we don't have the notion of homotopy. So what would be the notion of rationally simply connectedness? And for this, we can use the following fact from topology. We can observe that the ith homotopic group of X is actually isomorphic to the I minus first homotopic group of the loop space of X. And this result is basically the formal pushing around of the suspension and loop space adjunction. And mimicking this definition, which allows us to say that X is simply connected if and only if it is connected and the loop space is connected. We mimic this definition by saying that X is rationally simply connected if it is rationally connected and the space of rational curves on X is connected or rationally connected. And there is a series of results that shows that this notion of higher Fano actually establishes some parallel with the topological picture. Okay, so first I need to tell you what the space of rational curves is. So let's fix a Fano manifold and a general point on X and consider the variety of rational curves, like non-constant maps from the projective line to X that pass through this general point. And I say variety because in general, it's not going to be smooth. So it can have it will have multiple connected components, and they may be very singular. But inside this variety, we can pick an irreducible component of curves, which have minimal degree with respect to C1 of X. So if we take, it means that if we take the intersection of the image of this curve with C1 of X, this should be minimal. So because we originally assumed that X is Fano, the positivity condition on C1 of X ensures that this intersection will be positive. Hence, we can pick the minimal number among the values. And the fact is that the H, this component of minimal rational curves, will actually be smooth and projective, which makes it very nice to work with. And we can ask questions about rational connectedness for H. Okay, and here is a list of results that draw this analogy with higher connectedness. So if we fix number D, we say that D is the dimension of H, dimension of the space of minimal rational curves. Then the Jong and Starr prove that if X is 2 Fano, and with an assumption on D that it is at least 1, then there exists a rational surface through X. And by a rational surface, we mean a surface which has an open subset, which is an open subset of CP2. Then Carolina and Anna Maria prove a similar and analogous thing for 3 Fano manifolds with the dimension of H at least 2, that there is a rational threefold passing through a general point X. And they could not verify the case when H is just CP2, but they suspect that even in this case, there would still be rational threefolds passing through a general point. And they also prove that if X is 2 Fano and D is at least 1, then H is Fano. And the Picard rank of H is 1, except for 7 explicit possibilities that they list. And they also show a similar thing for 3 Fano manifolds. If D is at least 2, then H is 2 Fano, and we need that D is at least 2. Otherwise, it cannot be 2 Fano by our observation on the dimensions. And its Picard rank will necessarily be 1. And so you can see that it kind of recreates this topological picture of saying that if we have a space X that is, let's say, 3 connected, then its loop space is 2 connected. And in 2021, we proved that if X is a 4-Fano, the like H is at least 3-dimensional. And we make a mild numerical assumption on on H, then H is 3-Fano and pk rank 1. Are there any questions?
Are there examples of H with higher carbon?
So there only are examples in this case.
Oh, yeah.
And so they, and these examples actually occurred, and they describe them explicitly in their paper. And with further positivity conditions, there will be no examples like for higher pk rank H. And actually, it's a good question whether there are higher Fano manifolds of high pk rank and of high pk rank, because yeah, at this point, I don't think we know any. Any other questions? Okay, so this is 2 papers that our group has produced so far. So in this recent paper, we actually turn our attention to the case of toric manifolds, which are especially nice algebraic manifolds because they admit a very combinatorial description. And we study their Fano and higher Fano properties. And actually, there is a conjecture that among toric manifolds, the only 2 Fano are projective spaces. And we partially verify this conjecture, assuming that an open subset of X admits a P1 bundle structure. We show that in this case, the manifold is not 2 Fano. And actually, if you look at experimental data, for low dimensions, these would comprise the most of toric varieties. And so people believe that the conjecture is true, but if it is not, it will be so if it's not, it may be the first example of a higher Fano manifold of pk rank bigger than 1.
This is a recent result too, I guess, in 2023.
Yes. So we have just posted this paper, and it is submitted, but not accepted yet. Yes, I think 8 days ago. January 2nd. Okay. Yeah. So and this one, this paper has 7 authors and an appendix by an 8th person.
How did we do for time? Is that right?
Hmm?
Did you just crush it time-wise? How long is it supposed to be?
Do you have any questions?
What is your favorite result of that higher Fano stuff? It's a firm question. What do you think is the most surprising appealing to you?
So I would say that this sequence of results are about the analogy with topology, how like k-Fano implies that the space of minimal rational curves is k-1 Fano, is the most surprising, and especially because for every k, it is pretty much a check by hand, and so it's like really interesting that it holds up to 4. And I know there are some inequalities for higher k, but it has not been proved in general yet.
Okay. Is one way to interpret those like sequence of theorems like equivalent to saying like, oh, if a manifold is n minus 1 connected and its top cohomology vanishes and it's n connected? Is that kind of like bootstrap thing? Because being Fano is like a cohomological condition. But, right? It's about like vanishing of Chern plus.
Being Fano is saying that C1 of X is ample. So which means that a power of the determinant of Tx embeds our manifold into a projective space. Sorry, and what do you mean by homological?
Oh, just like it's coming from like cohomology classes. Things. I don't know. Like it seems like the flavor is like you decided like what n minus 1 connected means, and you want to like bootstrap it up to the next one. And it sounds to me kind of similar to like maybe something in the way of like a Hurevich result. Maybe that's not the right way to think about it.
I would say that it is an interesting question to ask, but I don't know of concrete results yet.
Is there something like if you're say n minus 1 connected and also I guess n-Fano, then you're n connected?
So right now, the only notion of n minus 1 connectedness, it would, like we can talk about homotopy groups of like the topology of the underlying topological space.
Yeah, but you're losing too much information.
That
when I said n minus 1 connected, I meant in the sense that you
that the space of minimal rational curves is n minus 2 connected.
Right. So you need to do the space of the space curves. One connected space of curves is connected. Two connected means the space of curves is the space of curves. Is one connected is connected.
So I would say no, because of the following example. So if we return to examples of Fano manifolds, here we have only blowups of up to 8 points. So if we blow up a 9th point, it will no longer be a Fano. But it is still rational.
what's the effect of blowing up on the space of rational curves? Is it very drastic?
Yeah, so actually for a general point, it doesn't change anything.
Okay.
Because away from the blow-up, you have just the same maps into your space.
But then that is a counterexample then, right? Blow up at 8 points, and then you know that this thing is going to be 0 connected, 1 Fano, but not 1 connected. Like blow up at 1 further point, then it's no longer. Oh, sorry. At 8. Yeah. I confused myself. Sorry.
Actually, maybe this would be a better answer to say that there are rationally connected manifolds which are not Fano. And so there's...
No, sorry, I was asking for ones that are Fano, rationally connected, but not 1 connected. Does that make sense?
Fano, rationally connected,
but not 1 connected. So their space of curves is not.
so you mean their space of curves is not Fano?
It's not rationally connected.
You need, I think, to permutation, you need Fano. That makes sense, right?
Yeah, but the original space is Fano. I would actually have to think about it. I don't know how to answer the question.
Okay.
It's a great question.
Well, I thought about the same.
This is neat. Are we thank the speaker again?
Yay. Thank you.
This was great. I really enjoyed it. It's cool.